Okay, for this chapter, we're going to look at the 2-sample t-interval and the 2-sample t-test. So recall, when creating the confidence interval, we do statistics, whatever the statistic is, plus or minus the margin of error. And we can kind of unpack that margin of error. So the margin of error is the critical value times the standard deviation of that statistic. And so for the t, we had the mean was our statistic, the sample mean, plus or minus t star, which is the critical value for the t, times s over root n. Now that we have two independent samples, our new formula is the x bar 1 minus x bar 2 plus or minus t star times the square root of all that, the s squared 1 over n plus s squared 2 over n2. Take the square root of all that. So the conditions for using the t-test. So again, independence within each group, simple random sample, independence between the two groups, and that our sample is not too big. This is almost never a problem, that our sample is too big. And that we sample from a nearly normal distribution, or our sample is bigger than 10. Or sorry, bigger than 30. So if it's bigger than 30, it doesn't have to come from a nearly normal, but if it's less than 30, then we need to. Okay, we're going to look at 3 examples. We're going to run a confidence interval and do a hypothesis test on each one of these. So each year, the U.S. Environmental Protection Agency releases fuel economy data on cars manufactured in that year. Below are summary statistics on fuel efficiency in miles per gallon from random samples of cars with manual and automatic transmission manufactured in 2012. Do these data provide strong evidence of a difference between the average fuel efficiency of cars with manual and automatic transmissions in terms of their average city mileage? Okay, so we're going to run a 95% confidence interval, and then we're going to run a hypothesis test to determine if there's a difference in fuel efficiencies. I've given you summary statistics here. So we'll do a couple examples where I give you summary data, and then I think one example where I give you the raw data. Okay, so I've given you, so we kind of glanced there. We have the mean, the automatic is 16.12, and the manual is 19.85. So there's obviously a difference there. I mean, the manual in our sample is greater. The question is, how likely is that to happen by chance? We know just from sampling variability that a different sample is going to produce a different result. So how likely is this difference going to happen just by random chance, if in fact they're the same? And that's what we're going to run a test to determine. And then we have a sample of 26 from both of these. Standard deviation looks roughly the same, 3.58 and 4.51. And I've given you the box plots as well. Okay, so I'm going to show you one using the formula, which we generally aren't going to do in here. And then I'll show you on the TI calculator, and then I'll show you on StatCrunch. Okay, so we're going to plug everything in. We're going to look at our table, and so we are looking at our T star here is going to be the 2.060. Again, degrees of freedom is the 26 minus 1. Okay, so we're going to plug everything in. So we got x1, which is 16.12 minus 19.85 plus or minus, and then we just plug everything in. I'm not going to read all that. When you crunch all this out, you get negative 3.73 plus or minus 2.326. So the 2.326 is our margin of error. Then you add that and subtract it, and you get an interval negative 6.056 to negative 1.404. Now you could have just as easily, if you would switch that and said 19.85 minus 16.12, you would switch what you called 1 and what you called 2. Those have been positive. And it's sometimes easier to express the positive. So this interval suggests that the mean difference in gas mileage of automatic cars is between 1.404 and 6.056 miles per gallon less than the mean gas mileage of manual cars. So on the TI-8384, if you're using that, you're going to press Stat, go to Test, select 2-sample T interval, put all the data in. You're going to get the same interval. In StatCrunch, we're going to go to Stat, T-Stat, 2-sample with summary. So you're going to enter in your summary statistics. We generally are not going to pull the variances in here unless you're doing a textbook problem, possibly in my math lab. You'll need to pull the variance. So if you happen to miss it and you didn't pull the variances, just go back and pull the variances. And so there is our our interval, which is exactly the same that we obtained when we did the TI and when we did this by hand. You might be off in the thousandths place just due to some rounding issues, but we should be okay. Now let's run a hypothesis test to determine if it's a difference. Okay, you're going to state HO and HA. So HO, there is no difference in fuel efficiency between cars with manual and automatic transmissions in terms of their average city mileage. HA, there is a difference in fuel efficiency between cars with manual and automatic transmissions in terms of their average city mileage. So again, the null hypothesis is always no difference. They are the same. So now we're going to run the test in StatCrunch. So it says find summary stats, create some visuals if you have not already. Okay, so we're going to do the t-test to sample with summary. We're going to push all that in. And notice we could have also expressed this null and alternative in symbols. We could have said mu1 either equals mu2 or mu1 minus mu2 equals 0. And similar for the HA, mu1 minus mu2 is not equal to 0. So this was a two-tailed test when we weren't sure which direction it was going to go in. So technically we set that up before we collect the data. All right. Once we collect the data, it's pretty obvious we probably should be going in one direction. But we set this up before we actually collect the data. Again, we generally don't pull variances. And we run this out, and we get a p-value of 0.0018. And there's our test statistic at negative 3.3. Okay, so now we're going to report this test statistic, p-value, and then make a decision with regard to HO. So either reject or fail to reject. And then an important part, be sure to state the conclusions in the context of the problem. So what do I mean by that? So here's our summary. Here's the summary of the two-sample t-test. Okay, so we're going to state the test statistic. So the test statistic is t equals negative 3.3. We've got a p-value of 0.0018. And so that's a pretty small p-value. So we're at the 0.05 level of significance. So we're going to conclude there is enough evidence to state that there is a significant difference in fuel efficiency between cars with manual trans and automatic transmission in terms of their average city mileage. Forgot the period there, should have a period at the end. Okay, so again, think about what this means. This is the same sort of decision that we were making when we just had one sample or when we had a paired sample. So we look at that p-value, very small. So the likelihood of these two being equal, given that we saw a difference of about negative 3.73. That was the average mean difference. So how likely am I going to see a difference that great if in fact these two are the same? Well, it looks like about 18 in every 10,000 samples, or about 2 in every 1,000 samples. That's pretty unlikely that would occur. That could have happened. That could be my sample. But most likely that's not. So I'm going to reject the fact that they're equal and say they're probably not equal. Example 2. A group of researchers are interested in the possible effects of distracting stimuli during eating, such as increase or decrease in the amount of food consumption. To test this hypothesis, they monitored food intake for a group of 44 patients who were randomized into 2 equal groups. The treatment group ate lunch while playing solitaire, and the control group ate lunch without any added distractions. Patients in the treatment group ate 52.1 grams of biscuits, with a standard deviation of 45.1. And patients in the control group ate 27.1 grams of biscuits, with a standard deviation of 26.4 grams. Do these data provide convincing evidence that the average food intake measured in amounts of biscuits consumed is different for the patients in the treatment group? And then run a 95% confidence interval and interpret in context. And then we're going to assume that conditions for inference are satisfied. So step 1, we're going to use the TI to do this real quick. And if you're not using TI, you can scroll through this. You're going to put in your summary statistics. Again, unpooled, and there's our interval from 2.3546 to 47.645. So this interval, with a degree of freedom of 33.9, suggests that the mean difference for food intake for treatment group is between 2.35 and 47.65 grams, more than the food intake of the control group. More than likely, you're going to be using StatCrunch, so go to tstat, to-sample with summary. Put in your summary statistics. Again, do not pool the variances. Confidence interval is at 0.95. And we get exactly the same interval, so the same interpretation, of course. So, hypothesis test. Do these data provide convincing evidence at the 0.05 level that the average food intake measured in amount of biscuits consumed is more for the patients in the treatment group? So again, state the HO and HA. So the HO, the average food intake, is the same for the patients in the treatment group and the patients in the control group. And this can be represented symbolically as mu1 equals mu2. And similarly, HA is the average food intake measured in amounts of biscuits consumed is different for the patients in the treatment group, not in the different, is different for the patients in the treatment group and the patients in the control group. Mu1 is greater than mu2. Okay, so we put in our summary statistics, set the hypothesis test. Since we're wanting to know if one of it is more, this is a one-tailed test, so we're going to say mu1 minus mu2 is greater than 0. Run the test statistic, run this, the two-sample t statistic, and we get a p-value of 0.0157 with a test statistic of 2.24. So p-value 0.016, that's less than alpha, so we're going to reject HO. The likelihood of a result this extreme occurring by chance is rare enough that we're going to say it probably didn't happen by chance, and there probably is a difference. So the average food intake is more for the patients in the treatment group and the patients in the control group. So mu1 is greater than mu2. The last example. Suppose an administrator wanted to determine if there's a difference in mean final exam scores between two different types, online versus on campus, of statistics classes at her university. She randomly selected 20 final exam scores here, and we're going to run a 95% confidence interval to determine if there's a difference between the scores, and we may even run a hypothesis test. Let's take a look. So on the TI-8384, we're going to go into L1 and L2 and populate both those fields. Run a two-sample T interval. Choose L1 and L2 for the list at 95%, again, unpooled. It's not safe to go into the water. Negative 4.409 to 0.31, roughly. So it does contain 0, so there's not enough evidence to conclude that there is a difference in the two mean final exam scores. In StatCrunch, you're going to go to T-Stat, two-sample, this time with data, and you're going to put the values from sample 1 in the online, and the sample 2 is going to be on campus. When you run it, you get exactly the same interval. And again, since 0 is in the interval, there's not enough evidence to conclude. Let's see if this is verified by running the hypothesis test. So again, HO, there is no difference in mean final exam scores between the two different types. Mu1 equals mu2, and there is a difference in mean final exam scores between the two types. So mu1 is not equal to mu2, a two-tailed test. And we're going to use 0.05 level of significance. So when you run this in StatCrunch, two-sample t-test, online for sample 1, on campus for sample 2, and run the test, make sure you again select the not equals to for the HA. And here is our summary for the two-sample t. We got a p-value 0.08, t statistic of negative 1.76. So this is, we're going to fail to reject, right? Because this is higher than our alpha level of 0.05. There's not enough evidence that there is a difference in the final exam scores between the online and the on-campus statistics classes. So I hope that helps.